Welcome back. Please recall, yesterday we have learned that almost any periodic signal xt can be written as a sum of sine and cosine signals with different frequencies. This infinite sum of sine and cosine terms is known as a Fourier series, where these individual sine and cosine signals are called harmonics, first harmonic, second harmonic, third harmonic, etc., depending on whether n equal to 1, 2, 3, etc. These coefficients n, bn, they are called Fourier coefficients. A0 in particular is the DC value or the average value of xt, and thus with this equation any periodic signal can be created by mixing sine and cosine signals with appropriate amounts. Now, to determine the required amounts of sine and cosine signals to create a given periodic signal, that means to determine the values of an, bn, a0, we need three formulas which we discussed and derived yesterday. A0 is the average value, n and bn are given by these two formulas. Now it is very difficult to remember three formulas, and therefore there is a simple way out so that we can work with only one formula instead of three, and we shall see that simple method trick today. So this is the Fourier series expression of a periodic signal xt. Let me write this as a0 plus summation over n equal to 1 to infinity an. In place of cosine, let me put e to the power j omega nt plus e to the power minus j omega nt whole divided by 2 plus bn. In place of sine, let me put e to the power j omega nt minus e to the power minus j omega nt whole divided by 2j. Now you may write this by collecting e to the power j omega nt from here and here together, e to the power j omega nt multiplied with an by 2 and plus bn by 2j. Similarly, with e to the power minus j omega nt, we have an by 2 here and minus bn by 2j from here. You may also write it as n minus jbn by 2 e to the power j omega nt plus an plus jbn by 2 e to the power, this should be minus j omega nt. Now let me expand this sum like this. A0 plus for n equal to 1, from the first term I will get a1 minus jb1 by 2 e to the power j omega 1t. Then for n equal to 2 we will have a2 minus jb2 by 2 e to the power j omega 2t. For n equal to 3, a3 minus jb3 by 2 e to the power j omega 3t, and so on. These terms are coming from this first term here. Now if you consider the second term, then you shall get, let me write here, plus a1 plus jb b1 by 2 e to the power minus j omega n is 1 t, then a2 plus jb2 by 2 e to the power minus j omega 2t, then for n equal to 3, 4, etc. Now let me put this minus sign here, and similarly let me write it as like this. Okay, and you have this long sum let me also do this. In place of a0, let me put a0 e to the power j omega 0t. E to the power 0 is 1, so I can do this. Now you see that this is a sum over many complex exponential terms, e to the power j omega 0t, j omega 1t, j omega 2t, 3t, 4t, here j omega minus 1t, minus 2, and so on. So that means I can write this as a sum over e to the power j omega nt, where n runs from minus infinity to plus infinity, all integers, plus, minus, 0, everything. And then these are multiplied with some coefficients, call them Cn, C for coefficients. So then it means A0 is defined as C0. This term is defined as C1. This term is defined as C2. In the same way, this term is defined as C minus 1. Because this is the coefficient of e to the power j omega minus 1t, then this I am calling as C minus 2, and so on. So the signal xt is written as a infinite sum of complex exponential signals e to the power j omega nt, and these coefficients are called complex Fourier coefficients. So that means that any periodic signal, almost any which satisfies Dirichlet conditions, can be written as a sum of complex exponentials, or almost any signal, any periodic signal can be created by mixing complex exponential signals. Now, the required value of this mixing coefficients Cn can be found from this A and B. If you already know An and Bn, then Cn can be calculated as An minus jBn by 2 if you already know An and Bn. And if you do not know, we will use the trick that we used yesterday. We shall start with the assumption that the signal xt can be written as a infinite sum of complex complex exponentials e to the power j omega n t with coefficient Cn, and then we shall multiply both the sides with e to the power, say, j omega kt. This is left side and the right side is this, e to the power j omega n t e to the power j omega minus kt. Now you can merge these two exponentials in one as e to the power j omega n minus kt Cn sum over all integer n's, and this is the left side. Now let us integrate both the sides with respect to time over a complete cycle. Okay, and then you can put the integration sign here over a complete cycle dt. Now I am telling you that among this infinite number of terms here, almost all of them will become zero and only one will survive. Which one? The one where n minus k is equal to 0. That means when n is equal to k. So I can write this as where n is equal to k. I need not sum over all the terms because most of the terms are 0. Only one term where n is equal to k is non-zero, and that is this term. So that means basically I have only one term, c k n equal to k e to the power j omega. In place of n put k, so that means 0, and k minus k is 0, dt integrated over a complete cycle, and then this is equal to 1, e to the power 0 is 1, so we will have this ck constant, and this 1 integrated over a complete cycle will give us t, and from this you can write ck is equal to the left hand side, which is this integration of xt e to the power minus j omega kt dt over a complete cycle, and then divide by this capital T. 1 over t times the left hand side. This way you can determine the value of ck for all k, 0, plus or minus 1, plus minus 2, 3, etc. Now let me also tell you why most of the terms in the summation is 0. For that, consider this integration cn e to the power j omega n minus k dt integrated over a complete cycle. Now this you can write as cn constant integration of e to the power j omega something is e to the power same thing divided by this coefficient j omega n minus k, provided this denominator is not 0. And then with the limits, so the integration is over a complete cycle, so we may put arbitrary limits like tau to tau plus capital T, and then this is equal to Cn, the denominator is a constant j omega n minus k, the numerator will be e to the power j omega n minus k, in place of t put tau plus t, then minus e to the power j omega n minus k, in place of t put tau. Then you can easily see that these two terms are equal, and therefore this is equal to 0. Or I can also write by replacing omega with 2 pi over t. Let me write n minus k first, and then 2 pi over t multiplied with tau and 2 pi over t multiplied with t. That's the first term, and minus e to the power j omega, let me write n minus k first, and then in place of omega put 2 pi by t multiplied with tau. Now it is clear that this dt cancels, and e to the power j, this thing is a periodic signal, you know, and therefore this 2 pi will have no effect. Okay, so these two terms are therefore equal and they cancel. This is equal to 0, but only if n and k are not equal. If n and k are equal, then here in this integration we cannot divide by n minus k or divide by 0. That's not possible. So here most of the terms are 0 and only one term that survives is that gives ck times t. So almost any periodic signal can be written as a sum of complex exponential harmonics, and to determine the amount of different harmonics, this is the trick we used. We multiplied both the sides with something and then integrated both the sides over a complete cycle, so that in the right hand side the effect of almost all the harmonics become 0 and only one harmonics survive. We are using this trick repeatedly, and this trick is analogous to the following experiment. Any arbitrary color can be produced by mixing three primary colors, red, green and blue. For example, red plus green creates yellow. Now suppose we have an unknown color and we want to know the red, green and blue components present in this color. We can do the following experiment. Now you see my computer screen from my perspective, and I shall use some color filters, red, green and blue, for this experiment. The red filter allows the red color to pass through it, and it blocks green and blue, or makes the effect of green and blue 0. And similarly, green filter allows only green and blue filter allows only blue to pass. Now to determine the amount of red in this unknown color, I shall hold this filter on top of this like this and adjust the amount of red until and unless I see both these two parts having equal brightness. I guess now the brightness is almost equal. So I shall note the value of red as 175. Remember the value. Now with the blue filter I shall do the same thing. I shall hold it here and try to match the brightness, and I shall note that value when the brightness is almost equal. Okay, so this value seems close to 100. Remember that. And now same thing with a green filter. I shall adjust the brightness. I guess now it is almost equal and the value is 133. Now let me mix red with an amount of 175, as we found green 133 and blue was about 100, and you see that these two colors matches quite well. So to determine the amount of one component, we are using filters to nullify or block other components, just the way here we are multiplying with something and integrating to make all other harmonics zero, effect of them zero, except only one harmonic. So almost any periodic signal can be written as a sum or mixture of complex exponential signals or complex harmonics, and the amount of different harmonics or these coefficients Cn is given by this formula. We have only one formula to determine this coefficients of complex harmonics. This is so simple that people call it complex Fourier series. Previously, we saw how to write an periodic signal as a sum of real valued sine and cosine signals, and now we are writing the periodic signals as a sum of complex exponential signals. The coefficients a and bn that we had earlier for real valued Fourier series and the new coefficients Cn that we have for complex Fourier series, they are definitely related to each other, as you can see from these definitions. Also, that we are writing xt as a sum of complex exponentials e to the power j omega nt with coefficient Cn in running from minus infinity to plus infinity. That means this is equal to C0 for n equal to 0 e to the power j omega 0 t, then plus C1 e to the power j omega 1 t plus C2 e to the power j omega 2t and C3 e to the power j omega 3t, so on. Also, for n equal to minus 1, we will have C minus 1 e to the power j omega minus 1t. Before that, C minus 2 e to the power j omega minus 2t and so on. Now let us group these terms together like this with this with this, and had I written more terms, then C minus 3 e to the power j omega minus 3t with C plus 3 e to the power j omega 3t. So let us group them, and now let us keep this term alone. C0 e to the power 0 is 1, and note that e to the power j something theta is equal to cosine theta plus j sine theta. So if you express exponentials into cosine and sines, then from here we will get cosine omega t minus omega t plus omega t are same, cosine omega t multiplied with c minus 1, and from here also we will get another cosine omega t, but that multiplied with c plus 1. Then from here we will get a sine omega t term, that is multiplied with c1, and there is a minus sign. Sine minus theta is minus sine theta, so minus j c1, c minus 1, and from here we will have a plus j c1. So these two terms we are getting from this and this term, that means from here. Now in the same way, from this term and this term we will get cosine 2 omega t multiplied with c minus 2, and from here c plus 2, and then sine 2 omega t with c minus 2 and a minus sign, minus j c minus 2 plus j c 2. These two terms are obtained from here, from here, that means this term and this term, and this way we will get more terms. This is nothing but xt. Okay, now let us compare this with our previous Fourier series expression as a0 plus a1 cosine omega t plus a2 cosine 2 omega t plus dot dot dot, and b1 sine omega t plus b2 sine 2 omega t, and so on. Now comparing this and this, you can easily recognize that c0 should be same as a0, and a0 is nothing but the average value of a signal xt. Then a1 is c1 plus c minus 1, a2 is c2 plus c minus 2. So in general, an will be cn plus c minus n, and b1 should be this, b2 should be this. In general, bn will be j, then we have c1 minus c minus 1, that cn minus c minus n. Complex Fourier series is actually simple. because you have to remember only one formula to get the complex Fourier coefficients, and then you can express any signal as a sum of complex exponential signals like this. However, if you really want to express a periodic signal as a sum of real valued cosine and sine signals like we did yesterday, and if you need to find the values of a1, a2, b1, b2, etc., often it is easier to actually find the coefficients Cn first, complex Fourier coefficients first, and then from the complex Fourier coefficients you can calculate the real Fourier coefficients an, bn, a0 using these rules. That is often easier. We shall see that with an example. Here is the square wave we saw yesterday with time period capital T and amplitude +1 -1, and now we want to write this square wave as a sum of complex exponentials. So we need to find the complex Fourier coefficients Cn, and for that we have derived the formula here. Okay, so Cn is equal to xt e to the power minus j omega n t integrated over a complete cycle and then divided by the total time period. You can choose a complete cycle starting from any point you like. For simplicity, let me take it from minus t by 2 to plus t by 2. Now let us do this integration. So for that, let me take 1 over t common and then write this integration in two parts. One is from minus t by 2 to 0, x t e to the power minus j omega nt. Another is from 0 to t by 2, x t e to the power j omega nt dt. Now from minus t by 2 to 0 in this region, the value of xt is constant -1. So you can put -1 here. And similarly, in this region 0 to t by 2, xt is constant +1. So you can write integration of this. Now integration of exponentials is always easy, at least easier than sine and cosine. 1 over t, then -1, and integration of e to the power minus j omega nt is the same thing, divided by minus j omega n, with limits minus t by 2 and 0, then plus 1 and e to the power minus j omega n t divided by minus j omega n with limits t by 2 and 0. Now this minus and this minus you can cancel. We will have 1 over t. Then j omega n, 1 over j omega n, and then e to the power 0 is 1, and minus e to the power minus j. In place of omega I will put 2 pi by t n, and t will be minus t by 2, so make it plus. Okay, then the next term, this minus, let's keep it here, then j omega n, and this is e to the power minus j 2 pi by t in place of omega, then n, then in place of t we have t by 2, and then minus e to the power 0 is 1. Now this t 2 goes away, and we have 1 over t, then j omega n you can write as j in place of omega 2 pi by t, n, that is common, and inside the bracket we have 1 and then another 1, so 2, then minus, take the minus common, here we have e to the power j pi n, and here we have another plus e to the power minus j pi n. Now this is equal to 1 over this t goes away, we have j 2 pi n, and here we have 2, and this is nothing but 2 cosine pi n. Now this if n is an even number, then this will be 1, so 2 minus 2 is 0, so we will get 0 if n is even, and if n is odd, then this will be 1 over j 2 pi n, then 2 minus minus 2, so that is 4. So this is what we get. Okay, that is the answer, but this is true if n is not equal to 0. Okay, see, n is this provided n is not equal to 0, because if n is equal to 0 here, then during the integration you cannot divide by n. Okay, so be careful about these small things that we often overlook. So for n equal to 0, we have to do it differently. So this is for n not equal to 0, this integration that we have done, and if n is equal to 0, then this will be 1, this will also be 1, and therefore these two will cancel and it will give us 0. Let me also write this for you. So this is for all n not equal to 0 and C0, that means when n is equal to 0, we will use the direct formula xt e to the power j minus j omega n is 0 t integrated from minus t by 2 to plus t by 2 1 over t, and this is equal to integration of xt, this is 1, so xt only, minus t by 2 to t by 2, and you can see xt is a odd signal, so plus minus area cancels and you will get 0. Now if we want to find the values of a0, an, bn, etc., let's look at this. A0 is C0, so A0 is C0 and C0 is 0, okay, and then AN is Cn plus C minus n. Now this will be equal to 0 if n is even, so this will be equal to 0 if n is even, and otherwise 4 by otherwise we have Cn, so that is 4 by j 2 pi n, 2 pi n plus C minus n, that is 4 over j 2 pi minus n, okay, if n is odd. These two are equal and opposite, so it is also 0, so an is always 0. And now bn is Cn minus C minus n with a j, you can see it here, and now this will be equal to 0 if n is even, because then Cn, C minus n both are 0, and otherwise we will have Cn is this 4 by j 2 pi n, then minus C minus n, which is 4 by j 2 pi minus n with a j if n is odd. So this you can write as equal to 0 for even n, and for odd n this j goes away, this becomes plus, and this will give us 4 by n pi. Now if you go back to your yesterday's note, you will see that we got exactly the same result. Complex exponential signals are not only good for solving complex maths, they do look quite pretty. Let me show you. Imagine this plane being a complex argand plane with this horizontal axis representing the real part of a complex number and the vertical axis representing the imaginary part of a complex number. Now consider a complex number z equal to e to the power j theta, which is same as cosine theta plus j sine theta. This number can be represented on this plane by starting from the origin, then move towards the right by an amount of cosine theta, and then move upwards by an amount of sine theta, and you will reach the point that represents this complex number z equal to e to the power j theta. Now the length of the line joining the origin and this complex number is given by the modulus of e to the power j theta, which is same as cosine square theta plus sine square theta equal to 1. And the angle of this line with the real axis is given by the angle of this number e to the power j theta, which is equal to theta. Now consider theta as a function of time given by omega t. Omega is a constant. Then this number z will also be a function of time given as e to the power j theta or e to the power j omega t. So this point will change its location on the complex plane as time changes. It will start from this position when t is equal to 0, and then as t increases, omega t increases, so theta increases, and therefore this point will move and the angle of this line will increase continuously with an angular velocity of omega. Now consider another complex function of time znt given as e to the power j in omega t. Once again, this point will move in the complex plane as time changes. It will start from this position and then it will rotate counterclockwise with the locus of the point always on the unit circle, and the speed of rotation will be equal to n omega. That means n times larger than the speed of z. If I represent these two numbers with two pens, this Zn being represented by the blue pen and Z being represented by the green pen, then when time is 0, they will both start from this position, and as time increases, they will both rotate counterclockwise, but the blue pen will rotate n times faster than the green pen, like this. Next, let us consider the complex function of time z minus t given as e to the power j minus omega t. Then this function will start from this position at t equal to 0, and then it will rotate clockwise, that means in the opposite direction, with an angular speed of omega. Now let us consider another function, complex function of time, call it z2t, which is a sum of two complex functions, e to the power j omega t plus e to the power minus j omega t. Now it has two parts. The first part, which I will show with this green pen, will start from the horizontal position and as time increases will rotate anti-clockwise with angular speed of omega. Then the second part, which I shall represent with this blue pen, will start from the horizontal position at t equal to 0 and will rotate in the opposite direction with the same angular speed of omega. Now if I show them together, so this is their starting position. If you add these two vectors, then you will get a number which is twice of them individually, which will be somewhere here, but that result will definitely be a real number. And then as time increases, green pen goes anti-clockwise, blue pen goes clockwise. Green pen is e to the power j omega t, blue pen is e to the power minus j omega t. But at any point of time, if you add these two vectors, then their imaginary parts are equal and opposite, they will cancel and the sum will always be a real number. That is evident because this you can also write as 2 times cosine omega t. Next, let us consider a number z, function of time, given as e to the power j omega n plus theta t plus e to the power minus j omega n plus theta t, which you may also write as e to the power j theta, a constant, multiplied with e to the power j omega nt, this part is a function of time, plus the second term e to the power minus j theta, which is constant, multiplied with e to the power minus j omega nt. This part depends on time. Now consider this part. It is a complex number, complex function of time. At t equal to 0, the value is e to the power j theta. So at t equal to 0, this part will represent a point somewhere here. And as time increases, it will move counterclockwise. But it starts from the angle theta instead of the horizontal position. Then the second part, e to the power minus j theta, e to the power minus j omega nt, this at t equal to 0 will be e to the power minus j theta. So that will represent a point somewhere here at an angle of minus theta, and then it will move as time increases in the clockwise direction with angular velocity of omega n. So therefore this and this together, let me show them with 2 pens. They start from this position. one at an angle of theta, another at an angle of minus theta, and from that position they will move in the opposite direction with the same angular velocity, and therefore at any point of time their imaginary parts are equal and opposite. So if you add these two numbers, you will get a real number. That is anyway evident because this is equal to twice cosine omega nt plus theta, which is a real function of time. Please note that here we had two complex exponential signals, one moving anti-clockwise, another moving clockwise. They have two coefficients, e to the power j theta and e to the power minus j theta respectively. Now if you look at these two coefficients, then you shall see that modulus of e to the power j theta is equal to the modulus of e to the power minus j theta, and the angle of e to the power j theta is equal to minus of the angle of e to the power minus j theta. The modulus of these two coefficients being same means that the radius of these two vectors are same. If they were not same, then they might have looked like this, one longer, another shorter. Also, these two angles are equal and opposite, means they start from a symmetric position. If these two angles were not equal and opposite, then maybe they would have started from such an initial position. And if those were the cases that the angles are not equal and opposite, or the modes are not equal and opposite, then when you sum these two vectors, their sum is not going to be purely real. Their imaginary components are not going to cancel completely. The sum of these two signals will be purely real if and only if the mod value of these two coefficients are equal and the angles of these two coefficients are equal and opposite, so that they start from a symmetric position. Which means for the sum of these two signals to be real, we need the coefficients to have equal modulus and opposite and equal angles. In other words, I can say that this and this two coefficients should be complex conjugate of each other. Complex conjugate. If they were not complex conjugate, then their sum will not be real at all the time. Now let us try to visualize complex exponential signals in a three-dimensional space. Imagine this horizontal line is the time axis and the plane perpendicular to it is the complex Argand plane. Vertical axis is imaginary axis and the axis perpendicular to the screen is real axis. Now consider a complex signal, call it zt, equal to e to the power j omega nt with some coefficient, where this coefficient c itself can be a complex number of the form, say, r e to the power j theta. Then at t equal to 0, z0 will be r e to the power j theta, which can be represented as a vector with length r and angle theta. And then as time increases, zt will have a circular locus rotating anti-clockwise in the Argand plane with the angular velocity omega n. And time is also increasing, so the tip of this vector will actually move in a spiral manner like this. Like a spring or a spiral, it will move like this. So this signal is periodic. It repeats or cycles again and again. This number omega n determines the speed of repetition. In fact, omega n gives us the angle through which the spiral rotates per unit time, and we call it the angular frequency, which has a unit of radian per second. Now if you divide omega n by 2 pi radian, then that is the frequency of this signal. That is the number of complete cycles or complete rotations per unit time. And that has an unit of hertz or cycle per second. And then the time period is equal to 1 over the frequency, which is 2 pi over omega n. And this number omega n together with j omega n is sometimes known as complex frequency, because this is a complex number and it essentially represents the angular frequency of this signal. Now, when we write any periodic signal xt as a sum over Cn e to the power j omega n t using Fourier series, complex Fourier series, then these individual components, individual periodic complex exponential signals, they are called the harmonics or complex harmonics or harmonic components of xt. First harmonic, second harmonic, etc., depending on the value of n equal to 1, 2, etc. So using complex Fourier series, almost any periodic signal with arbitrary shape or pattern can be written as a sum of periodic complex exponential signals with different angular frequencies omega n, where n runs from minus infinity to plus infinity. Now we have learned that almost any periodic signal xt can be written as a infinite sum of complex exponentials C0 e to the power j0 omega t, C1 e to the power j omega 1 t, C2 e to the power j omega 2 t. On the other side, C minus 1 e to the power j omega minus 1 t, and so on. Now you notice that these terms occur in pairs. Here e to the power j omega minus 1 t is a signal that rotates with an angular velocity of omega in the clockwise direction, and this is a signal which rotates in the opposite direction but with the same angular velocity. Similarly, these two signals, one of them rotate in the clockwise direction, another in the anti-clockwise direction, but this and this have same angular speed, and the angular speed of this or this is double compared to this or this. And you can determine the value of these coefficients C0, C minus 1, minus 2, plus 1, plus 2 with this formula. Cn is equal to integration of xt e to the power j minus j omega nt dt integrated over a complete cycle, any complete cycle, whole divided by the time period. Now suppose x is a real valued signal. That means x takes only real value, which is true for any practical real life signals. We have never seen a complex signal in a real life. Voltage signal, current signal, speed, position, anything can take only real value. So if x is a real valued signal, then you observe that Cn is given by this, and C minus n will be given by let's put a minus sign here, by this. Now you see that Cn is equal to Cn star complex conjugate. Why? Because x is a real number, t is a real number. This is the only complex part in this integration. Now taking Cn conjugate means conjugating the right hand side completely, but conjugate of t is just one of same as it is. Then conjugate of x is x, because x is also real. But conjugate of e to the power minus j omega nt will be e to the power plus j omega nt. We need to put a minus sign wherever we have this j. And you see this is same as this, C minus n. So this means C1 is equal to C minus 1 star, which also means C minus 1 is C1 star. Then in the same way, C minus 2 is C2 star, and so on. That means if you consider, say, these two signals which are rotating like a spiral with opposite angular velocity, their coefficients are complex conjugate of each other. That means they will start from a symmetric position like this, theta and minus theta. The radius for both of them is same, and then they will rotate in the opposite direction, one in the counterclockwise direction and the other one will rotate in the clockwise direction, like this. So that at any point of time their imaginary components are equal and opposite and will cancel each other. So the sum of these two signals will always be real. Okay, sum of this plus this is always real, sum of this plus this is always real, and they all occur pairwise. So that's all for today.